Synthetic fuels are often positioned as the primary drop-in solution for decarbonizing aviation and the entire heavy transport sector. The problem isn't the chemistry. We know how to make clean fuel. The challenge is that the physical properties of these molecules are in a constant tug-of-war with the economics of building their supply chains. The industry is chasing a very specific profile, a molecule with high energy per kilogram, high energy per liter, and the ability to be stored at ambient temperatures. But achieving those exact traits requires a staggering logistical footprint, demanding 17 distinct industrial steps just to bring a single drop to market. To evaluate the true return on investment for synthetic fuels, we need to map out this manufacturing chain and determine exactly where your company should position itself. Surviving the energy transition means matching the rigid physical realities of these fuels with grounded, highly specific business strategies. Every logistical hurdle in this market stems directly from the physics of energy storage. Specifically, it comes down to energy density, the measure of exactly how much power you can pack into a given amount of mass or volume. There are two ways to measure this. The first is gravimetric energy density, which tells you the amount of energy per kilogram. The second is volumetric energy density, tracking the amount of energy per liter or cubic meter. Both are critical for transport. This matrix compares our fuel options. Raw hydrogen starts as our baseline input, and it holds an immense amount of energy per kilogram. But hydrogen presents a massive spatial challenge under normal conditions because its energy per unit of volume is extremely low. To actually transport it, you have to invest heavily in compression or liquefaction. To solve that volume problem, producers chemically convert raw hydrogen into liquid synthetic hydrocarbons. This combination works. Synthetic hydrocarbons retain that high energy per kilogram while achieving high energy per liter, allowing for ambient temperature storage and rapid refueling. The trade-off for achieving these metrics is steep. Producers now have to source captured carbon dioxide and engineer a vastly more complex chemical synthesis process. By solving the storage and transport limitations of raw hydrogen, you directly create a massive logistical burden on the manufacturing side. Moving out of the laboratory and into the market, we can map exactly what that burden looks like. This diagram outlines the 17-step value chain required to produce synthetic fuel, divided into 3 distinct zones: upstream, midstream, and downstream. The upstream phase starts with securing vast amounts of inputs, requiring renewable project developers, grid or transmission companies, and dedicated industrial water suppliers. Next, you need electrolyzer manufacturers and hydrogen producers to generate the raw base molecule. Moving into the midstream phase, the transformation requires separate CO2 capture companies and specialized CO2 transporters to deliver the necessary carbon. Building the facility itself requires highly technical fuel synthesis technology providers, heavy industry EPC contractors, and the ultimate plant owners. In the downstream phase, the raw fuel moves to product upgraders for refinement, and then into specialized storage terminals. The physical journey finishes with fuel distributors delivering the product to final end users, like airlines, shipping lines, or industrial customers. Finally, this entire physical process is wrapped in critical support steps: certification bodies, carbon accounting and verification providers, plus lenders and insurers managing the capital risk. If a single company attempts to own this entire chain, they retain total control over the final product and capture all of the retail margins. However, that vertical integration demands unsustainable capital expenditure and operational risk. Practically no single entity can execute all 17 steps profitably today. Total integration is a fast track to financial overextension. The most viable path forward is surgical specialization within a specific section of this map. For executive leadership, deciding your company's competitive position should be strictly dictated by the assets and core competencies you already have in place. This decision tree maps exactly how to route your company to its optimal role. If you are a tech-heavy startup, your primary assets are likely strong intellectual property and software capabilities. Your optimal position is either as a technology licenser or a carbon management platform provider. By taking this route, you avoid massive infrastructure costs entirely, but your revenue becomes dependent on partner adoption and integration. Alternatively, traditional fossil fuel incumbents possess entirely different assets: primarily existing midstream refineries and widespread downstream distribution networks. Their most profitable decision is to operate as a refinery partner or a product marketer, capturing immediate value near the end of the supply chain. By strictly leveraging existing strengths, companies can extract solid value from synthetic fuels without exposing themselves to the chaotic, capital-intensive middle stages of production. There is one final major player: renewable energy operators with existing solar or wind farms. These operators should utilize massive physical assets to act strictly as renewable power suppliers or project developers. This position secures steady, predictable business-to-business offtake agreements, deliberately sacrificing the lucrative retail margins found in the finished fuel. The high energy density of these molecules is an industrial ideal, but don't let that utility mask the logistical complexity of producing them. Pick a highly specific niche in the chain, secure specialized partners for everything else, and build a defensive moat.